Okay, so on Wednesday, I introduced the three methods. How can we have the pressures? And then I emphasize most important thing, you need to know the elevations at your locations. If you don't know the altitude, you cannot have the pressure in accuracy. Okay, so the next one, the slide show the three types when we discuss the pressures, the three units we need to know. So as showing here, the first one is absolute, and usually we use the PABS. Okay, and the second is the gauge, and we use the P gauge. Okay, and the final one is the vacuum, and we use the P vacuum. And the slides just put the words and try to provide the interpretations of the absolute and the gauge and the vacuum, but the quite difficult to understand. So I emphasize here, you can focus on the formula showing here, and you will actually know why we call that is the gauge. Okay, so the first one, the P gauge. So you will have the absolute pressure and the minus PATN. That indicates the pressure right now in here relatively to the environment pressure. The PATN is the like right now. I have the pressure on calculators and compare to environment pressure. Okay, so usually we call that the P gauge. The P gauge, the absolute pressure relatively to PATN. And you see the vacuum is the minus of the P gauge. So the vacuum is the PATN minus PABS. Okay, so you need to keep in mind, maybe just pick up at least one. For me, I will remember the P gauge. And the P vacuum is minus P gauge. Okay, so maybe you are still confusing, and then this is a cartoon figure. You see the bottom line showing here. You have the bottom line, and you see the bottom line. We call that is absolute zero. Okay. And the second, the middle line in here, we call that is local atmosphere pressure. It is the same as right now, environment pressure. It's a 1 ATM. So, and I highlight 2 points. The one point is A point in here. Another point is B point. So if you see the A point, you can measure the absolute pressures relatively to the absolute zero, right? So you know that the red line, vertical red line, is equal to the number shown here, the 301 kilopascal absolute. And if you change it to the PSI unit, and you will use the PSIA. The A indicates the absolute. If you use the K part, you will have the ABS on later. Okay, so this is the number showing here is absolute pressure. So you can, if this absolute pressures minus the local pressures, it indicates the gauge pressure, right? It's equal to the gauge pressure. So the 301 kilopascal here minus 1 101.3 kilopar is equal to 20. 200 is kilopar, right? Okay, so for this example PA, you actually know how can we compute the gauge pressure and how is the absolute pressure for the A point. And if you focus on another point in here is the PB, and the PB clearly is lower than 1 ATM, right? Is the PB in here is lower than 1 ATM in here. So you see the gauge pressure of the B point is the minus because the absolute pressure lower than 1 ATM. And you see, as I mentioned, the vacuum pressure is minus of the gauge pressure. So since the gauge pressure is minus, so the vacuum pressure is positive. Okay, so this is a figure provide an opportunity to better understand the definitions between the gauge and the vacuum pressure. Okay, so we have the very quick exercise. As the example showing here, please convert the 5 PSI vacuums to absolute pressures and in SI unit. Okay, so the SI unit, we need to convert the unit to be the Newton and the meter cubic, right? But right now the unit in here is the pressure unit is the PSI is equal to the bomb force divided the inch square. Okay, and then right now we only have the a vacuum. So how can we have the absolute pressure? So actually the P vacuum is equal to the P ATN minus the P absolute, right? So very simple. If we follow this formula, we reorganize the equations. Indeed, the PABS is equal to PATN minus P vacuum, right? So you just put a number inside. The PATN I highlight in here is equal to 14.7 PSI minus the P vacuum here is the 5 PSI, and you know that the answer is 9.7 PSI, and all of the numbers shown here is the absolute. So the final answer is related to the absolute pressures. It's our purpose, absolute pressures. Okay, so you know the formula, so you can compute the absolute pressure very quickly. But if you didn't know the formula before, you cannot understand the answer of this example. But the final questions, we need to convert the PSI into the SI units. So you actually know 1 ATM is equal to 101.3 kilopar, right? And it's equal to the 14.7 PSI. So you can convert by yourself. The number showing here is smaller than 1 ATM. So you can convert how many kilopar you have for this PSI value. Okay, so actually you can convert like you can 9.7 divided the 14.7 and multiply the 101.3 kilopar, and the unit will convert to the kilopar. Okay, so you can use your calculator to double check the answers. Okay, that's the answer is the same as the upper corner show the number in here, the same is 66.8 kilopar. Okay, so it's our final answers. So basically this question is quite simple, but if we don't understand the formula and the definitions before, for this question we cannot answer, right? So that's I emphasize the three important pressure units: absolute, vacuum, and the gauge. And usually for engineering problem, we use the gauge pressure because the gauge pressure is relatively to the environment pressures. Okay, so the next ideas is the differential pressure. Okay, so as you see the this is the tube, the pipe, and we have the 2 points, and the 1 point is A, another is the B, and we actually know the flow is flow from the left to the right. So we guess the pressure at the location A is high, right? It's higher pressure at the location A, and there is a lower pressure at the location B. That's why the flow will start from the A to B, because the high pressure will flow to the lower pressure. Okay, so for that case, we know actually the delta P is positive because the flow is start from the left to the right. Okay, so that's just the basic ideas. If we have the pressure difference, and the flow will, the material fluid will start to flow. If there is no pressure difference, the material fluid will stay on there. Okay, so if we have the pressure difference, the fluid will start to flow. Okay, and then this is very important ideas, as I mentioned, introduced before. The mechanical advantage, and we usually call that is the hydraulic machine. And you see the bottom figure showing here. If I tell you actually the P1 point in here, maybe I use the yellow dot, and this is the point 1, and the area of the closed tube is A1. And we have another point in here. We call that is the point 2, and the area of this tube is A2. And I tell you the P pressure at the location 1 is equal to the location 2 pressure. And based on these simple equations, you know the pressure 1, we have the force, right? So we have the force 1 divided the A1 is the pressure 1. And that will be equal to the pressure, the force 2, and divided the A2. And this example tell you if I apply the small force 1, F1 is smaller force, and then we can have the larger resulting force F2. And the reason why show that because based on the equation showing here, you actually know the F2 is equal to F1 multiply the ratio between the A2 and the A1, right? and sometimes the A2 is larger than A1. So the ratio in here is larger than 1. So you can provide the small F1 force, and then we will have the output force F2 is larger. Okay, so this is behavior is similar to the changing thing, right? So, but this idea we call that the Pascal principle. That's because if I push the force in here, and the delta pressure changes will propagate through all fluid inside, and the pressure change propagate all directions on the fluid material, and the result is with the same magnitude. So in all of the areas located at the fluid, because this is a confined fluid, so the delta, the pressure change propagate all fluid material with the same force magnitude, and for all directions. That's why I can say the point in here and the point in here, they have the same pressure. So the P1 is always equal to the P2, and they are located at the same elevations. Okay, so this is a Pascal principle. Okay, so if we apply this idea to the real case, so we have the exercise showing here. We have a large force in here. So I plot the horizontal line in here, and I have the external force F1 acting on this point, and the F1 actually the exercise tell you the F1. The F is the 100 newtons. So here I write down the number 100 newton push in here, and there are the point C in here. As you can see, there is a C, the point in here. So we can have measure the length. The length in here is the 30 centimeters plus the 3 centimeters, so it's equal to the 33 centimeters, and this is equal to 0.33 meter. Okay, so we know the distance between the force and the C point. Okay, so in this problem, we need to consider the moment balance. So the force acting in here, we will have you apply your right hand, and you can try to understand the moment is clockwise or counterclockwise. Okay, so the force in here, we will have the moment like these directions. You can check by your hand. Okay, the force is downward, and the length is go to the left. Okay, so you can use it by your hand, right hand. So you know that the moment in here, I use the M, is the positive moment. Okay, and if you focus on another point in B, this is the B point showing here. Okay, and because you would like to apply the force downward, and we will have a relatively force upward at the B locations. So in here, we have another force is upward FB. Okay, and the length between the FB and the C, we actually know is 3 centimeter. Okay, so here we have the 0.03 meters length between the FB force and the C. And we can check by our right hand, and we see it's a clockwise moment, so it's a negative moment in here. So we use the moment symbol. We call that is MB, and the MB is minus, and the M in here is positive. So in this systems, the first balance, the moment should be equal between the M and the MB. Okay, so our first idea for these questions, sum of the moment should be equal to 0. Okay, so we have the M and we have the MB. They are equal. Okay, so we can put the number inside. How can we have the moment M? Because we already know the force is 100 Newton, and the length between the force and the C point is 0.33 meters, and is equal to the moment B. But the moment B, we didn't know the FB right now. So I use the parameters FB in here, but we know the length is 0.03 meters. So based on this equation, we can find out how large of the FB force. Okay, so I check from the number based on my calculator. So it's it's equal to the 1100 Newton. Okay. So we go back to see the questions. The questions is not required to answer the FB force. We need to know the F2 force. Where is the F2 force? And the F2 force acting in here. So how can we have the F2 force? If you base on the Pascal formula, if you remember, we actually assumption the point in here 2 and the point in here 1, the pressure are equal. Okay, so this is the Pascal ideas, and then so we know that what is the F2, because the pressure are equal, so F2 divided A2 should be equal to FB in here, the FB in here, the force in here is FB, and divided the A1, right? And we already know the FB values, and we can rearrange the equation. The F2 is equal to FB force multiply the ratio between two cross-section areas. Okay, and the figure already tell you the diameters of the A1 is the 1.5 centimeters, and the diameter of the A2 is 5 centimeters. Okay, so you have the diameter, so you can replace the ratio between the area by the diameter. So here, this is the A1. So in here, we know that the D2 divided the D1, and because of the area, so here we have the square of the diameter ratio. Okay, so we put the number inside. Maybe I change it to here. So we put the number, the F2 is equal to the 1100 Newton FB force, and the ratio here, the D2 is the 5 centimeters, and the D1 is 1.5 centimeter, but we have the square because the area is proportional to the diameter square. Okay, so we can compute the answers, okay, by your calculator. So the 5 divided 1.5 and the square and multiply the 1100 newtons. So the answer is around the 12.2 kilonewton. Okay, so this is a quite a simple exercise, but the idea for this exercise, we need to have the moment balance first, and we can calculate the force acting on A and B locations, and then we use the Pascal principle ideas and to find out the final force we want, F2. Okay, so if you do the comparisons, we only use the 100 newtons, but finally we can have the 12.2 kilonewton. It's totally different numbers. So this is the efficiency. It's due to the hydraulic mechanisms ideas. Okay, so we move to the next, and the later we are focused on the hydrostatic equation. So we need to introduce the hydrostatic condition first. Okay, so I emphasize again, for the hydrostatic, let's indicate there is no acceleration. Okay, if you have some fluid start to flow, but the fluid flow with a constant velocity, there is no acceleration. Okay, no acceleration indicates no velocity gradient. Okay, so I would like to emphasize. And then the second, because we don't have the velocity gradient, so there is no viscosity force. Okay, because based on the viscosity equations, the viscosity provided shear stress is proportional to the velocity gradient. Okay, so no velocity gradient, no viscosity force. So we only have the force we need to overcome is the normal force, normal pressure. The normal force is caused by the weight of the fluid. The weight of the fluid. So as the cartoon figure showing here, maybe you have the fluid particle in here. And then you see the bottom force. This is the bottom pressures. And this is the upper pressures. And you based on the length of the arrow, you see the arrow on the bottom is larger than the top. Okay? That's because on the bottom of the fluid, we need to overcome more weight from the fluid. So that's why the bottom will have the higher pressure, but the upper part is lower pressure. Okay? Only one difference is the weight between two locations. Okay, so this is a body force diagram to tell you this is the net force of the pressure. It's larger than the pressure upper. Okay, so if based on this idea, so we only have if the flow start to the fluid start to flow with a constant velocity, that indicates there are the pressure difference only. So the fluid can start to flow, not caused by the shear stress. It's just caused by the pressure difference. Okay, so we have the maybe cross section in here. We have a higher pressure, maybe this is 0.1. Again, so we have the high pressures, and then we have another cross sections in here, and then we call that the 0.2, and this is a lower pressure. So the flow with the constant velocity, okay, and then we put the tube, but you see the tube is open. We put one tube in here, and you can see the fluid will have a rising high, delta Z. If you have the fluid with the flow speed and cross through this tube, and you will observe the delta Z rising. Okay, so that indicates the pressure difference in here between the P2 minus P1 is indicated the pressure difference between the 2 and the 1 is equal to what kind of fluid you use. So the density multiplied the G is the specific weight, right? Is the gamma, and the delta Z. You multiply the deflections. This is the deflection high, delta Z, and then this is the pressure difference. Okay, so only one difference is caused by the how fast of the flow speed. If the flow speed is higher, that means the pressure difference is high, and then we will see the relatively higher the delta Z. Okay, so this is one concept to us to better understand the delta P is related to the delta Z, and also depend on what kind of the fluid you use. Maybe you use the oil or water or seawater, they will have a different higher. Even though you have the same pressure difference, but the different fluid have a different delta Z. Okay, so this slide we would like to derive the hydrostatic equations, and the answer already showing here. The dP divided the dz is equal to the minus gamma. The dP is the pressure change related to the elevation change. The ratio is equal to the minus gamma. So based on this formula already tell you the concept, what kind of concept. The most important is the minus here. Why the minus here? That's because if you increase your elevations, but the pressure should be decreased, right? If you increase the elevations, but the pressure will decrease. So that's why there is the minus symbol here. Okay, but we need to derive these formulas by ourselves. So right now we would like to derive the equations. So if you focus on the right hand side, so I define, I have the one line, and I tell you this line, the directions we call that the arrow factors, and this along the cylinder centers, the direction on the right is the positive. Okay, so the right hand side of the arrow factor is positive. Okay, and as I mentioned for these equations, all of the force, because right now is the hydrostatic, so some of the net force will equal to 0, right? No force, that means no accelerations, because due to the static conditions. So our first assumption is the force along arrow directions is equal to 0. The force along the arrow directions is equal to 0. So you need to find out how many forces you have along the arrow directions. So the clearly force in here is the weight. Okay, is the weight the weight is downward. The weight is caused by the water cylinder. Okay? And if you need to project the weight into the plane on the arrow directions. So right now we can project the force weight into the horizontal force like this arrow showing here. Okay, so this is the project force from the weight Fw, and the direction is negative arrow directions. Okay, and we know that the angle in here is the alpha. It's alpha angle. So we know that the Fw showing here is the weight multiply the sine alpha, right? Multiply the sine alpha. Fw is equal to the weight multiply the sine alpha. And if you focus on two cylinders, the bottom and the top, we have the external pressures. So we have the external pressures. So the second force is the pressure force. So we have the pressure force, Fp. Maybe I use the Fp. So the Fp should be equal to the P multiply delta A as showing here, okay? And the direction is the right hand side. So it's the positive force. And if you focus on another force in here, should be the minus P plus delta P and multiply the delta A. Delta A is the cross-section area. But why we use the delta P here? Because the flow already moved. So that indicates there are some pressure difference. So I use the delta P in here. Okay, so you arrange the equation in here is the P delta A minus P delta A minus delta P multiply delta A. And the final, you know, the two items will cancel out. Okay, so we only have the delta P multiply delta A. So we only have the two forces along the arrow directions. One is the pressure force. Another one is the force caused by the fluid weight. Okay, so we can go back to here. And that's based on the force balance. We know that the W minus the Fp need to minus the W. Maybe I use the minus the Fw is equal to 0, right? And we already know why I use the minus, because I know the Fw showing here is negative arrow directions. Okay, so I can put the answer, the delta P multiply delta A is equal to Fp, and the minus the W and the sine alpha, it will equal to 0. So what the W in here? Okay, what the W in here? Oh, sorry. So we know that the W, we have the W, okay? And we know that the W is equal to the gamma multiply the volume, right? And we know that the volume is equal to delta A multiply delta L, right? Because the delta L is the length, and the delta A is the area in here. So we know the volume is the delta A multiplied the delta L. Okay? And how about the sine alpha? If you see here, based on the figure showing here, the right hand side, you know that the sine alpha is equal to delta L over delta Z. Delta L over delta Z. So you put the rate watts, the information put back to the force balance equation here. So you can rewrite the equation. It's minus delta P multiplied delta A, and the minus the weight is the gamma delta A delta L, and the sine alpha is the delta L over delta Z, and it's equal to 0. Okay, I use the, okay. So, and you just cancel out some parameter, they are the same, like the delta A. So we cancel out the delta A, and the delta L also cancel out. Okay, so you can reorganize the equation is the delta P is equal to the gamma delta Z. Okay, and I just move the negative symbol to the right hand side, and the delta D put to the left hand side, and it's equal to minus gamma. Okay, so only one difference in here is there is the differential, but here we are the delta. We use the delta, so we can assume the delta Z is quite smaller. The delta D is quite smaller. That means the changes between the cylinder, the elevation changes is smaller. So we can rewrite it close to the dP dZ and equal to the minus gamma. Okay, so we prove this is very important. This is the hydrostatic differential equations. Okay, but the concept is quite simple because the elevation increase and the pressure will decrease. That's why we have the additional minus symbol in here. Okay, elevation increase and the pressure will decrease. Okay, so this is a hydrostatic differential ideas. And if you notice that we have the assumptions for these equations is until now we assume the density can be changed. The density can be changed. But I always emphasize for the liquid, the density didn't change it. Maybe changed the volumes, but it's quite smaller. But for the gas, the density can be changed because if you apply the compression force, the gas will the volume of the gas will decrease, right? And the volume change, the density will also change. Okay, so based on the hydrostatic differential, we derive the equations, but we assume that this is the formula showing here is assume the gamma will change it. The gamma will change it. Okay, but the next slide I showing here, the next step we assume the gamma is constant because due to the constant density assumption. Okay, so if the dP dZ equal to minus gamma, if the density didn't change it, so that means it's equal to constant, right? This is equal to constant values. And then we can do the integrations for these problems. and then we see what happens for these equations. Okay, so right now I would like to do the integration. So I move the dz to the right hand side, minus gamma and the dz. And then this is, I assume I start from the P1 to P2. The pressure is from the P1 to P2. And because the gamma didn't change when the elevation changed, so I put the gamma outside and the integration operator in here. And we have the Z1 to Z2. The elevation changed, and there is the Z, the differential elevations. Okay, so we just expand the integrations. So we know that it is the P2 minus the P1 is equal to minus gamma and the Z2 minus Z1. Okay, and you just expand. There is the minus gamma Z2 plus the gamma Z1, and then you put the one together and the two together, so you can reorganize the equation is equal to the P1 plus gamma Z1 is equal to P2 plus gamma Z2, and we know that the final should be equal to a constant. That indicates if the liquid with the same densities. So the P1 is the pressure, right? And the gamma Z1 is the pressure related to the elevation. Because we locate at the different elevation, we have the different pressure. Okay, so usually we call that is piezometric pressures. We call that the PZ. This is the constant values is equal to the PZ. And we call that is the piezometric pressure. Okay? We call that the PZ in here is the piezometric pressures. And we call that the P is the pressure, and the gamma Z is the pressure caused by the elevations. And if this equation, if we totally divided the fluid gamma, we can divide the fluid gamma. So the P plus gamma Z is equal to constant, and we totally divided the gamma, so the equation to be the P divided gamma plus the Z is also the constant. But usually we use the H. We call that is the head. The head. So the Z in here is the elevation head. And the P divided gamma, we call that the pressure head. And the right hand side H, we call that is the piezometric head. Okay, so the Chinese, we always say that is 压力水头, 高层水头. And the right hand side H is the 侧压水头. Okay, so this equation, why can we say that is the constant? That's because the condition satisfy the constant density. So if at the same, you have for the one liquid, but you have many points located on the liquid inside. Any point, the piezometric pressure are the same. Any point located on the liquid, the piezometric pressure are the same. Okay, if the constant is density. Okay, so in the following class, we will have some exercise, and you will know how the idea and how can we apply the hydrostatic equation to the real case. Okay, so that's the figure showing here. Just tell you observe the two different fluid, right? The first one is the upper one is oil and the bottom is water. So the idea is because the oils, there are 3 points E, F, D, and the 3 points located on the water is C, A, B. And you see, the sentence showing here HC is not equal to HD. H is the piezometric head, right? Why they are not equal? Because the HC is here and the HD is here. They locate at the different fluid. Different fluid, liquid, will have the different density. So they are not the same. Okay? So I can say that the HF is equal to HE and equal to HD. Is right. It's correct, right? Because the FED, they are located at the same fluid with the same density. But not equal to HC over HB and HA, right? Because A, B, C points located at the water. And I can say also HA is equal to HB and equal to HC. It's also correct because they are the same. They are the water and with the same density. Okay, so that's the idea for the constant density assumptions if you apply the hydrostatic equations. Okay, maybe we start here and we have a 10 minutes break. Okay, 这个很重要，就是只有在